Starting today, we begin our focus session on stochastic processes and probability theory uh, for fractional operators. The first speaker within this focus session is Professor Luisa Beghin. She is a full professor in probability and mathematical statistics at Sapienza University in Rome. She obtained a PhD in methodological statistics from Sapienza University in 2000. Her current research interests are primarily in stochastic processes linked to fractional calculus and non-local operators, Levy processes, subordination, and time change theory. We are very happy to have you here, Professor Beghin. You may please begin your talk.
Okay, thank you very much, Pavan, and thank you, Arran, for invitation, and thank you all of you for participating. So I have already shared the screen, so I think you can see now the screen. I hope so. Yes.
Yes, we can see your screen.
Okay. Sorry, just to be sure. Okay, so as Pavan already said, I was invited, and my intention is to speak about the connection between stochastic processes and the theory of fractional operators, both in the standard sense. I will introduce very well-known operators such as the Riemann-Liouville and Hadamard fractional derivatives and integrals, but also in a generalized sense. But probably many of you know already also these generalized operators. As the title, as indicated in the title, I forgot to tell that this talk is based on two different papers, one with Lorenzo Cristofaro from Luxembourg University and Yulia Mishura from Kiev University, and the other one again with Lorenzo and with Federico Polito of Torino University. I will try to describe both, of course, without going into details. And in these two papers, we introduce the definition of these stochastic processes in an infinite dimensional space. But then we move to finite dimensional characterization of the process, these new processes, in order to study their trajectories, properties, and so on and so forth. So, just to have an idea of what I will present, of course, I will start with some notation and definitions. The basis of both the two topics is the complete monotonicity property of some functions. And then the relationship with Laplace transform of functions. And based on this, we can define, but it was already well known in the literature, the definition of gray noise spaces, which generalize, of course, the white noise setting. Then we will be able to define as generalized processes some objects in these spaces. And in order to define these generalized processes, we will make use also of fractional operators. And then, of course, I will give, as I said, some definition of this kind of these different kinds of fractional operators. And these I call preliminary results. And then I will try to describe two different extensions of so-called fractional Brownian motion in two different directions. The first one is what we have called the Bernstein Brownian motion, or Bernstein fractional Brownian motion. then, of course, I will explain in which sense and why this word Bernstein, because as is written here, we define this process by means of either convolution type derivative or convolution type integral, which are generalizations of fractional derivative or integral. And these definitions are given in terms of Bernstein function. And then we will analyze some results on this class of processes, and in particular some asymptotic results on variance and covariance and the behavior of these processes in terms of memory properties. So we will see that in the first case, when the definition is through convolution type derivative, they have short range dependence, while in the second case, they will display long memory property. And then some hints on ongoing research. And then I hope to have enough time to show also another different direction of research that we are carrying out and one paper is already finished, but we are working in another extension. But this direction is in terms of not convolution type derivative, but in terms of Hadamard derivatives. And then the process that we define, we have called it Hadamard fractional Brownian motion, because it is a generalization of the fractional Brownian motion in terms of obtained by means of Hadamard derivatives and integrals. And in this case, we can apply this definition both in the white noise space, where, of course, there is a Gaussian measure defined on this space. Otherwise, we can generalize it in gray noise case by means of the so-called Leroy measure. I will show you later. And then again, some hints on what we are still doing in this second topic. Okay, so as I said, a central notion of a central basis for this kind of analysis is the complete monotonicity property of function, of central function. So I recall that function f is completely monotone if it is C infinity, and the derivatives alternate sign with this rule. And then, but the most important thing is the representation of a completely monotone function f in this as integral, apart from these two terms that in our case a and b will be zero. So we can say that our completely monotone function will be exactly the Laplace transform of a measure mu, and this is why we are so interested in complete monotonicity. Of course, examples of completely monotone functions, the most simple, the simplest one is for example, the negative exponential. And using this first completely monotone function, we can define the Gaussian measure. While if we use more general functions, such as the Mehta function with negative argument, or x here is positive, or the upper incomplete gamma function, both of them, the Mehta and the upper incomplete gamma function, are completely monotone. And then we can define, as we will see in a minute, we can define different kind of measures and then of noise space, white and gray noise. White in the case of exponential, and then of Gaussian measure, while in the other two cases we have gray noise measures. So just to introduce also the space where we are defining these measures, as it is common in this kind of literature. I will give later some reference for the gray noise analysis. The space is often chosen to be, the space of function is chosen to be the Schwarz test the space of Schwarz test functions, which are functions that are infinitely differentiable and rapidly decreasing when the argument goes to infinity. And we will denote by S prime its dual, and then it is well known that this inclusion of spaces is holds, where L2 is the L2 space with the Lebesgue measure of R with the Lebesgue measure. So then, if we denote by F, a big F, completely monotone function on this space, then the key theorem of this theory is the Bochner-Millos theorem, which allows to say that there exists for any function, completely monotone function F, a unique functional phi, such that phi of psi is defined as as f of squared norm of psi, and this is in L2. And this phi identify a unique probability measure mu, which of course depends on the on which phi is chosen, and then of which f big F is chosen. So, for example, if, as I said before, if we choose big F to be the negative exponential, and phi of psi then becomes e to the power minus square norm of psi, then the space we will refer to will be the white noise space, because the corresponding measure mu is, as it can be seen here, this phi is the characteristic functional of the Gaussian measure, and then the space will be with this choice of F, of big F, will be the white noise space. In the other cases, for example, if big F is the Mittag-Leffler function with parameter beta, beta is in 0, 1, then we get the characteristic functional of the so-called gray noise measure, and then we will indicate it as mu with parameter beta, and so on and so forth. For example, in the paper that I will cite later, we have defined what we called a gamma gray noise space by means of by choosing as completely monotone function f, big F, the upper incomplete gamma with parameter rho. Rho again is in 0, 1, and then we defined this measure mu rho, and then the space can be called gamma gray noise space. Of course, we must introduce also generalized processes, stochastic processes on this space, and we use the definition of this kind of process that was the first one that, as far as I know, which introduces this kind of, which started this kind of literature was Schneider in 1990, and then there were many other authors, Da Silva and Grothaus and many co-authors that worked on these kind of definitions. Our paper written here is for the gamma case. the incomplete gamma case. Anyway, in all these cases, for all these probability spaces, you can define a generalized process by means of the dual pairing. Actually, the dual pairing between S and S prime is extended to the dual pairing between S prime and L2. So, for example, function phi can be chosen to be, since it is in L2, can be chosen to be the indicator function of the interval 0t. And then in this way, if the measure of the space is the white noise measure or gamma measure, then the generalized process defined in this way is the very well-known standard Brownian motion. In other cases, if you use in the space, you use the Mehta-Gleffer, the measure defined by means of the Mehta-Gleffer function that I've shown in the previous slide, then again choosing the indicator function as an element of the space, then you have the definition of the so-called gray Brownian motion, or for other choices of mu, of course, you have different processes. But both are generalizing the standard Brownian motion, because the Mehta-Gleffer and the incomplete gamma functions respectively for beta equal to 1 or for rho equal to 1 coincide with the negative exponential. And then you are back to the standard Gaussian case. But in these three cases, with these three definitions, you do not include a memory in your process, and then in order to introduce a memory property in the definition of the process, in some sense, they defined, for example, in the Mehta-Gleffer case, Mainardi and other authors defined the so-called generalized gray Brownian motion by defining the process, instead of simply as this dual pairing with the indicator function, they introduced here, in front of the indicator function, they introduced the fractional operator, a fractional operator which can be either the derivative, the Riemann-Liouville fractional derivative. In this case, the definition here is given in terms of right-sided, from x to plus infinity. Alpha is always in 0, 1, or in terms of Riemann-Liouville fractional integral. So with this, defining this operator, general operator, fractional operator in this way, then the process defined by means of this dual pairing, and where here you have this Riemann-Liouville fractional derivative or integral, is a generalization of the fractional Brownian motion. So introducing this fractional operator, of course, you get, instead of generalization of Brownian motion itself, you get a generalization of the fractional Brownian motion. Okay, I do not care so much, I do not spend time on constants and so on. Here, this is a way of defining the characteristic function of the process. And what is easy to see, in particular, we can see it from the covariance that probably is written later, but also from the characteristic function here, you can see the dependence of the characteristic function. In the first case, it's the process is defined on the white noise space, so with respect to a Gaussian measure. And then here you have the characteristic function of the fractional Brownian motion. While if you use again the measure so-called gray measure, then defined by means of the Mittag-Leffler function, then you have here the characteristic function of the so-called generalized gray Brownian motion. And in the last case, here the measure is again the gamma incomplete, the measure defined by means of incomplete gamma function. And then here you have the characteristic function of a generalization of the fractional Brownian motion. But what happens here for the covariance actually in the three cases? I reported here only the case of the gray Brownian motion, generalized gray Brownian motion, but also in the case of in the gamma case. Then you have that the memory property of the process remains the same as in the fractional Brownian motion case. On the right, you can recognize the covariance of the fractional Brownian motion, which is simply multiplied by a constant which depends on beta. So the property, the long memory or short memory, depending on alpha in 0, 1 or in 1, 2, of the fractional Brownian motion is not changed by this definition because this the measure, the choice of the measure only affect this constant in front of the standard covariance of the fractional Brownian motion. The processes are self-similar with stationary increments. And in the case of the generalized gray Brownian motion, it is, no, I forgot to put the reference here, but in a paper by Mainardi and Pagnini, it is proved that the marginal density function of the process is the fundamental solution of a stretch time fractional master equation. And okay, there are many results on this generalized gray Brownian motion. As I said, we were interested in some extensions of these kind of models. And then the first direction that we have chosen together with Lorenzo, Christopher, and Julia Mishura was obtained by replacing the fractional operator in the definition of the process in front of the indicator function by means of a more general operator, which is obtained as a convolution type operator. So this is defined in the general, so-called general fractional calculus. I referred here to the papers by Kochubey and also Toaldo and so on. Now there are many others. And here I put the definition of the convolution type operator that we have used, that in the derivative case is given by generalization of the Riemann-Liouville fractional derivative, but instead of having here the normal power alpha to t minus x to the power alpha minus 1, we have instead the tail of a Levin measure. So I will indicate a Levin measure by n bar, and its tail, which means the integral from x to plus infinity, as this name. And then, of course, if the standard Riemann-Liouville case is obtained when you choose the Levin measure of a stable subordinator, because in this case the Levin measure is x to the power minus alpha minus 1, and then again here you have the power and the power of t minus x. For the definition of the inverse operator, the integral operator, it is, if, for example, in the paper by Kochubey, you can find the definition of the integral, which is obtained by means of the so-called Sonine associate kernel of this Ni. So it means that this function k, which generalizes, of course, the power alpha of the standard Riemann-Liouville integral, is in this relationship with Ni, with the Tail-Levy measure Ni. So they are linked by this relationship. Of course, there must be some assumptions are satisfied, but I do not go into detail. So some assumptions must be satisfied by Ni and then also by K. So, and then in order also to explain why then we called the generalized process that we defined, we called them Bernstein Brownian motions. This is because both the Tail-Levy measure, the Levy measure itself, of course, and the Sonine associate kernel K are defined by means of Bernstein function. In fact, if we recall the definition of a Bernstein function, in particular this definition of Bernstein function, then you see here that the Bernstein function G can be expressed again, A and B in our case will be equal to 0, can be expressed as this integral of the Levy measure in particular, and then of course by taking the Sonine associate kernel K, we can define also the integral. Then here I also wrote down the expression of Fourier transform of the generalized fractional derivative. Here Ni, as I've shown before, is not a power. It is this derivative is defined with a kernel by means of a kernel which is Ni, while the integral is defined by means of a kernel which coincides with this K. So this is why they are inside brackets. And this is again the relationship between the derivative defined by Ni and the Fourier transform of the derivative, and which is expressed by means of this Bernstein function G. And the Fourier transform of the integral is expressed by means of 1 over G evaluated at Ixi. Okay, here I put the special case that I described before. If we choose this Bernstein function G with parameter alpha, and then the Tail-Levy measure is s to the power alpha minus 1 divided by 2 with this constant. And then we are back to the Riemann-Liouville fractional order derivative or integral if instead of using the Tail-Levy measure, we use the associate kernel of this Tail-Levy measure. Okay, so the first result that we had to prove is that applying this derivative, this general derivative, or the general integral, fractional integral, to the indicator function, then the indicator function, okay, we had to give some condition for which these are well defined, and these are conditions basically very basic condition on the Bernstein function G. So not all the Bernstein functions are useful and can be adapted to our case, but okay, these are not very restrictive conditions. And then it is possible to obtain in an explicit way the derivative of an indicator function of an interval. And then we had to prove that the derivative of the indicator function under some condition that we had to consider, then the derivative of the indicator function is in L2. Because as I said before, we are defining the process as a dual pairing extended to S prime and L2. And then we have to consider a function in L2, to have a function in L2. And then under this condition, A1, A2, on the Lévy measure Ni bar and on the Tail-Lévy measure Ni, the derivative of the indicator function, general fraction derivative of the indicator function is in L2. And again, for the case of the integral, we have considered this different condition on the K, which is, as I said before, the associate kernel of Ni, and K, which is the integral between 0 and x of the kernel K, kappa, sorry, kappa and K. Okay. So under these conditions, we are able to okay, I will skip this slide in case I will come back later. We are able to describe and to define in a rigorous way this generalized process in this using, as I said before, this dual pairing extended to L2. This I put here the definition of the process where when the process is defined by means of the Bernstein function G and then by means of the derivative, while in the other case, as we have seen before, we have the 1 over the Bernstein function G, and then the operator here will be the integral one. Okay, here in this part, the measure on the space is the standard white noise measure, while in the future we are planning to extend this analysis also to the non-Gaussian case, so for more general measures. But so far we are in the Gaussian setting. So we can, of course, obtain some expressions for the covariance of the process. Of course, this depends on the Bernstein function chosen here, G. And we will see later some special cases. And also we have obtained some results on for example, on the Holder continuity of the sample paths of the process. And of course, again, the Holder continuity of the sample paths depend on a condition which is in terms of the Bernstein function chosen, the chosen Bernstein function G. In particular, the sample path continuity follows by this upper inequality. I mean, this upper limit to this integral, while if this lower bound is satisfied by the Bernstein function G, we can say that the corresponding process has local time continuous with respect to t, almost everywhere with respect to x, and square integrable with respect to x. So again, the sample paths properties are given in terms of conditions on the Bernstein function G chosen. There is also another way of representing the process. Unfortunately, here I forgot to change the notation, so the process is always the same, even if I have used here a different notation because it was taken from a previous version of the paper. But apart from this, we can represent what I have called the Bernstein Brownian motion in the so-called Mandelbrot-Van Ness representation as a stochastic integral with respect to the Wiener process, two-sided Wiener process here. And again, if the Bernstein-Brownian motion is defined by means of the derivative of the general fraction derivative, and then by means of the Tail-Levy measure, then we have this representation of the process, which holds for all the finite dimensional distributions, apart from a constant here. As you can recall, again, if Ni is in the special case where instead of general tail of Levy measure, you have the tail of the stable measure. And then here, instead of Ni, you have the power alpha or alpha minus 1 or alpha minus 1 over 2. Then you are back to the Mandelbrot-Van Ness representation of the fractional Brownian motion. But here, this representation is for a general Tail-Levy measure, Ni. And analogously, in the integral case, we can write the Bernstein Brownian motion as a stochastic integral where the kernel is the associate kernel of this Ni. Again, we can give some properties of the process by using this definition. It can be seen easily that the increments are stationary. And also we can describe some special cases. Of course, as I said, when we refer to the stable case, then we have this first representation, which is the Mandelbrot-Van Ness representation of the fractional Brownian motion, but by choosing different Bernstein function G and then the corresponding Levy measure and Tail-Levy measure, then we can obtain other well-known processes as special case. For example, the so-called tempered fractional Brownian motion, which was studied in this paper by Mershayet and Sapsica, and many other processes that can be defined. For example, with this choice of G, we can obtain an alternative tempered fractional Brownian motion. Here the kernel is quite complicated because it's given in terms of incomplete gamma function again. And so on and so forth. We can obtain also a Ornstein-Uhlenbeck representation of Mandelbrot-Van Ness representation of the Ornstein-Uhlenbeck process. But in this case, we have a particular situation because in this case, the Levy measure here I put, in this case, the Levy measure and the Tail-Levy measure coincide. And but as you can see, they are finite on 0 plus infinity, and thus in this case the derivative has a non-singular kernel. So it is a strange case here in order to obtain the Ornstein-Uhlenbeck process. So as you know, probably they cannot be defined properly as a fractional derivative, but as a general operator. Okay, so as I said, we were interested in studying the asymptotic behavior of the variance and covariance of the process. And in particular, we were able to see that this asymptotic behavior of variance and covariance change with the choice of the Bernstein function and the corresponding tail-Levy measure. Then we were able to prove that, for example, we have these two different asymptotic behavior of the variance. If Ni, so the chosen Levy measure and then the tail Levy measure is in L2, then we have that the variance of the process for t tending to infinity is constant, while on the contrary, you have these two different limits for the variance and for variance divided by t. And asymptotic and the variance tend to plus infinity. Moreover, we have that for when the process is defined by means of the derivative, we have that this rho n, which is the moment, mixed moment of the covariance in some sense of the increment, is always negative, and then we can say that the process is not persistent, and it is also short-range dependent, since we have that this sum is finite. On the contrary, when the process is defined by choosing by using in the definition the generalized fractional integral, then we have an opposite situation. The process is persistent and long-range dependent, of course, for a choice of k that satisfies the assumption that we have assumed. So now, of course, we are still working on some other results which concern the definition of the noise of the process. So we have called it, of course, the so-called Bernstein noise, because we call this process as Bernstein process. But I will not go into detail on this. In this case, as you can see, we must define and evaluate the so-called S transform of the process, and this is given in terms of the operator of the general operator, but the left-sided general derivative, and so on. Okay. We also studied the Ornstein-Uhlenbeck so-called Ornstein-Uhlenbeck-Bernstein process, which is obtained by solving this ordinary differential equation. And then, well, here we have again the left-sided generalized fractional derivative, and then we were able to evaluate the covariance of this process, which is quite complicated expression. Well, this h, where this h here is given in terms of, again, of the tail of the Levy measure chosen. And now, as I said before, we were planning to extend this analysis also to a more general measure. We can call it gray noise measure, so extending the Gaussian case to a non-Gaussian setting. Of course, this can be more complicated, and then we can study again for this process. We will probably will be able to give conditions under which we get some properties, different properties of the process. Okay, but this is what we are planning to do, and we didn't do it so far. So in the last 10 minutes or even less, I will just give some hints on the second direction. So I will not go into many details, but just to describe a different direction that that we are using now, and we are trying to develop now. In this case, we were trying to substitute in the definition of the process, substitute the Riemann-Liouville operator, M, as if you recall, in some cases is the, in one case it is the fractional Riemann-Liouville derivative. In the other case, for alpha, different values of alpha, is the Riemann-Liouville integral. And now we were interested in looking what happens if, instead of using the Riemann-Liouville operator, we use a standard operator, well-known operator, which is the Hadamard operator. Now, of course, I will show you the definition of the Hadamard fractional integral or derivative. But in this case, we also generalized the underlying measure, which is not the white noise measure. Well, we started by using the white noise measure and then generalized it to the so-called Leroy measure. Probably I will not go into details on this more general setting, but just for your curiosity, why also to describe why we have chosen the so-called Leroy measure. This is because the Leroy measure, which is again a completely monotone function, it is the solution. It is well known that it satisfies the following equation, where here we have the Hadamard derivative. Here the Hadamard derivative is in the Caputo sense, okay, but it is Hadamard-type derivative. And then we were trying to reproduce the situation that for the generalized gray Brownian motion we have for the Mittag-Leffler function, which is the solution, which is the eigenfunction of the Caputo fractional derivative. In some sense, the role of the Mittag-Leffler function for the Caputo fractional derivative is played here by the Leroy function, which is simply a generalization of the exponential, where here in the denominator, instead of the standard factorial, you have the power beta of the factorial. Usually the Hadamard derivative is associated, if it is used in partial differential equation. There are some papers also by Polito, Singer, and Garra, and other authors. This derivative is usually associated to ultra-slow diffusions. But in our case, since we are not referring to the use of, we are not introducing the Hadamard derivative in partial differential equation, we are using the Hadamard derivative in the definition of the process itself, as I will show in a minute. Then what we obtain, quite surprisingly for us, is that we do not have even diffusion. Not only we do not have ultra-slow diffusion, but we have standard diffusion. So the effect of using the Hadamard derivative vanishes in the one-dimensional characterization of the process. Of course, it will not vanish in full characterization of the process, and so for example in the covariance. Okay, but I will try to show it later. First of all, I just recall the definition of Hadamard integral. Here we will use beta in 0, 1. The case beta in 0, 1, then also the Hadamard derivative is simpler because this nth derivative in our case is the first derivative in front of the integral. And then here you can see that instead of having in the Riemann-Liouville case, you have z minus t to the power beta minus 1. Here we have logarithm of z minus logarithm of t to the power beta minus 1, and the same for the analogous situation for the Hadamard derivative. Then, of course, at the beginning we followed similar steps that I described for the other extension. So we studied we applied the derivative, the Hadamard derivative and integral to the indicator function, and see under which condition they are in L2. In order to use then this result here for the definition of our what we call Hadamard fractional Brownian motion. Of course, here we were expecting that introducing this operator, we could have memory different properties of in terms of memory of the process, but we also expected to have an anomalous diffusion, as it was for the, for example, in the Gray Brownian motion case. But this is not the case, as I will show in a minute. As I said also before, introducing this Hadamard fractional derivative or integral, depending on the interval for alpha. If alpha is in 0, 1, we will refer to a derivative, fractional Hadamard derivative. If for alpha in 1, 2, we will refer to a fractional integral derivative. Anyway, in both cases, the one-dimensional distribution of the process is the same as in the as for the Brownian motion, apart from constant. Okay, but as you can see that, for example, here I put the first characteristic of the process that we have obtained. Since here we are still considering Gaussian measure, the distribution is a Gaussian with 0 mean, and the variance is exactly the same as in the as for the Brownian motion. It coincides with that of the Brownian motion, but the covariance is very different here, and it is different also from the covariance of the fractional Brownian motion. It is expressed in terms of these Tricomi confluent hypergeometric function, so it has a rather complicated expression, but you probably know that this kind of function is already plotted and can be plotted even by Wolfram alpha, by many other instruments, and then it is not complicated also to obtain some plots and some to see, and also to simulate trajectories. The simulations, okay, I skip all this. This is not very important. I just say that we proved that the process is still semi-similar, but with index 1, not alpha, and has non-stationary increments. This is new for this kind of process. And this kind of processes, and this is the distribution of the increments. I have already said that now there is no effect of the Hadamard operator on the one-dimensional distribution. We don't have an anomalous diffusion, okay, and we can still prove some properties of sample paths and trajectories. And also we have proved that the process is always anti-persistent if alpha is in 0, 1, and then it is defined by means of the Hadamard derivative, while for alpha in 1, 2, it is always long-range dependent. And this must be proved by means of this quantity and of this sequence, because in this case the increments are not homogeneous. Finally, just to say that, for example, in order to simulate the trajectories of the process, then you have that it can be useful, this kind of Mandelbrot-Ness representation for that also for the Hadamard fractional Brownian motion, but of course here, instead of having the power, or in the general case the Levy measure, okay, here I indicated the Levy measure by eta instead of ni, but it's the same. We have here the logarithm of the ratio between t and s. And okay, simulation can be done by using this representation of the process. Now we are also carrying out some other research on this topic, for example, studying the process which converges weakly to this Hadamard fractional Brownian motion, which can be defined by means of shot noise process with slowly varying response function and other kind of results. So I think I can finish. I can stop here. I hope that there. Okay. Sorry, I put again my slides. These are the papers that I more or less described during this presentation. Only one is already published. And then here, some other reference on generalized Gray Brownian motion, and yes, on the also convolution type derivatives. I forgot to put also the paper by Kochubey, but it is very well known. Probably you already know. Okay, so thank you very much for your attention, and so please let me know if there are questions or.
Thank you very much for the nice talk, Professor Beghin. I invite the audience to kindly raise their hand for the questions. So I'll call out your name and you can unmute your mic as they appear on my screen. Okay, I do not see any raised hands, so I'm assuming there are no questions. So is there any final comment or remark that anybody wants to give? You may unmute your mic and go for it. All right, there doesn't seem anything. So thank you for Professor Beghin for the nice talk. It was very nice having you.
Thank you for the invitation. Thank you very much. And for the organization, as I said, very, very useful for us and interesting. Thank you very much.
The pleasure is ours.
Also Arran and the other participants.
The pleasure is ours. Thank you very much.